All right, today's lesson is on using parametric equations to model the motion of objects. So we're going to start with this problem about some pools in a boat. So all three remote control boats can move at 4 feet per second. Asuka, Ben, Chelsea are each playing with one. They're at different positions. So Asuka's boat A is here 10 feet up, and it is moving east. Boat B, Ben's boat, is here 5 feet up, and it is moving west. And Chelsea's boat is 5 feet over. And for our purposes, we are going to make this point right there 0, 0. Whenever we're doing parametric, we need a coordinate system, we need a reference point, we need an origin, and that's going to be that corner right there. Okay, so let's think about first a table to create the graphs. So write parametric equations after we fill in our table. So boat A, Asuka's boat, is going to move this way at 4 feet per second, just like this. So after 1 second, it will have moved 4 feet. After 2 seconds, it will have moved 8 feet, and so on. And so we can fill in the table like so. So at 0 seconds, it's at 0 feet, and then it will go 4, and it will go 8, and 12, and 16. Now its y value is a constant. It is always going to be 10 units high. So we can fill 10s in there, and I can come up with the parametric equations. The x equals has a y-intercept of 0 and a slope of 4. So I could do 0 or just 4t. At any time, my x-coordinate is 4 times the time. The y-coordinate is a constant of 10. All right, let's go back and think about boat B. So Ben's boat is starting at an x-coordinate of 25, because it's 25 feet, and it is moving back this way at 4 feet. So if we think about its table, so it starts with an x-coordinate of 25, and it moves back at 4 feet per second. So we go to 21, 17, 13, 11. And its x-coordinate has a y-intercept of 25, and then we are decreasing 4 feet per second. Now its y value, it is constantly 5 feet high, and so I can write y equals 5. Now our last boat, Chelsea's boat, is not moving horizontally, it's moving vertically. It starts at an x-coordinate of 5, and that x-coordinate will remain the same. And it's the y-coordinate that will be going up by 4 for every second. So the x-coordinate starts at 5, and it stays at 5. Its y-coordinate starts at 0 and goes up by 4. And so we get the equations x equals 5, y equals 4t. Now we're going to throw a little wrench into the situation. There is a wind blowing from west to east at a rate of 3 feet per second. So now, if we think about boat A, this is going to make this move more quickly. Every second, it'll move the 4 feet, but the wind will push it another 3. So at time 0, it's at position 0, but at 1 second, it's now moved 7 feet. And at 2 seconds, it's moved 14 feet. At 3 seconds, 21 feet. And our general equation will be x equals 7t, the 4t plus the 3t. The y is still the same. The y is always 10. And so our y equals 10. Boat B, Ben's boat, is also affected, but now the wind is blowing against its motion. So it starts at its position of 25. It's going to move forward 4, but the wind will push it back 3 for a grand total of 1 forward, or actually backwards in this case. And then it goes to 23 and 22. And so its x equation is starting at 25 and going back 1t, and its y is constant at 5. Okay, oops, there we go. And then finally, boat C, Chelsea's boat, is a little bit trickier. But what's happening? So it starts at position 5, 0. 1 second later, it's horizontally moved 4 feet. Or I mean vertically, sorry, that's vertically. It's still moved 4 feet. And after that, it'll move another 4 feet and another 4 feet. So that part doesn't change. But what is the problem is that it's going to be moved horizontally as well. So instead of staying a constant of 5, at 1 second, it will have been pushed 3 feet to the east. So it will be at 8, and then another 3 feet, and then another 3 feet, and then another 3 feet. And so its x equation is now 5 plus 3t, and its y equation is 4t. Okay? If I want to graph this, if I want to look at this picture, so let's make the pool. So our pool is 10 high and 25 wide. So if I go to my window, I want an x min of 0, an x max of 25. Let's go up by 5. A y min of 0, a y max of 10. And what about our time? How fast will or how long do I need for the longest one? Well, that's going to be boat B is going to take the longest time since it's fighting the wind. It's really only moving 1 foot per second. And so to go 25 feet is going to take it 25 seconds. So I want to see at least 25 seconds to see all of boat B's motion. Now if I put my equations in, my first, let's see, so 7t and 10. And one cool thing is I'll come back and do that at the end. Boat B is 25 minus t and 5. And then boat C is 5 plus 3t and 4t. And if you make these, the bouncing balls, or not bouncing, but the moving balls, if you pick that option, we can actually see the motion of our boats, which is pretty cool. And I also need to be in simultaneous mode, otherwise they'll go one at a time. But if we go to mode and we go down to simultaneous, boom, when I hit graph, there go my boats. Oops. I must have put boat A way too high. Oh, it's a total of 15 feet. That's the problem. So my pool, I'm going to stop this, is not quite high enough. My y max should actually be 15. And now we'll see what's going on. So there's our motion, which is pretty cool. All right? Now I want to think about the motion of boat B or boat C a little bit more. All right? So let's explore that a little bit in a little bit more detail. So how far does boat C travel in the first 3 seconds, and what's its velocity? So if we think about this, it starts here at 5, 0. 3 seconds later, so it goes over, well, each second it travels horizontally 3 feet. So it goes a total of 9 feet there. And in 3 seconds, it's going 4 feet per second there. So it goes 12, right? This is my 3t. This is my 4t. How big or how far or what is that distance? Use the Pythagorean theorem. And I get 9 squared plus 12 squared is c squared. And that turns out to be 225 is c squared, or c is 15, which should make sense if you understand your Pythagorean triples. This is a 3, 4, 5 triangle multiplied by 3. So what is its velocity? Well, it went 15 feet in 3 seconds, so its velocity is 5 feet per second. And so if you see this as a 3t, 4t, this would be a 5t. There again are our Pythagorean triples. Now we can also ask at what angle with the bottom of the pool does boat C travel? So I want to know that angle right there. Well, using my sides, I know that tangent of theta is 12 over 9. And so if I am in degree mode, not radian mode, I can get that angle. So let's do inverse tangent 12 over 9. And it's traveling at an angle of 53.5 0.13 degrees. Now I'm going to take that angle and I'm going to store it in alpha A. I like to store things. I think I'm going to use that later because I have one more question to ask about this. I want to write a new equation using the velocity and my angle. So if I know that my boat is traveling at 5 feet per second, what is the horizontal component? And this is 53 degrees. What's my horizontal component and what's my vertical component? And we have shown that this right here is going to be 5t cosine 53, and this is going to be 5t sine of 53 degrees. And if I go to my y equals, and we'll try one more. So let's try it. Whoops. I want to be right there. So if I do 5t cosine, and I'm going to use alpha A because that is this more than 53 degrees. That's my exact angle. And I do 5t sine of alpha A. I want to add one thing because my boat starts, I'm going to insert a starting position of 5 for x, and then where I go. And if I look now at my table, and let's unhighlight the ones above it, so all I see is this last one, and this one. Oh, I don't know if I'm having an effect. Let's look in the table. What do I get? So there's my first equation. That's boat A. There's boat B. So it's this last table right here. And there is my 5, 0, 8, 4, 11, 8. So that does also match the exact same motion. All right, let's try one more problem. So where's the plane? So we have a plane. Memphis is 1,000 miles due west of Albuquerque. And we have a plane traveling 250 miles per hour, like this. But we also have wind blowing from the north at 20 miles per hour. Okay. Where is the plane after 4 hours? So 4 hours traveling in this direction, it will be 1,000 miles due west. But we have to remember, we've also traveled this distance. So in this direction, I've gone 250 t, but in this direction, I've gone 20 t. So I'm 80 feet, 80 miles south of where I wanted to be. Okay, so this is where the plane will end up because of those two combined motion, the horizontal motion and the vertical motion. How far did the plane actually travel? Well, this is our right triangle. I traveled 1,000 feet here, and I traveled 80 feet, 20 miles per hour or 80 miles per hour. 20 miles per hour for 4 hours is 80 miles. And so I want to know this. This is a Pythagorean problem. Again, I want to find the square root of 1,000 squared plus 80 squared. And I will get 1003.194896. So that's how far we actually went. Now if I want to know the ground speed, so I want to know the speed in relation to the ground, I take the distance we traveled and I divide by my 4. So if I take this and I divide by 4, the plane was actually traveling 250.798 miles per hour. What was the bearing? Well, the bearing will be found by actually finding that angle first. And so I can think about, here's my opposite, here's my adjacent. Tangent of theta is 80 over 1,000. So theta is going to be tan inverse. And that is Oops, that's over 100. Let's try that again. Need one more zero. 4.57 degrees. Okay. Now that's the angle that's the angle below 270. I want the bearing, and if I know this is 4.57, I take 270 and I subtract, or I can say negative that answer plus 270. And I get a bearing of 265.4. Okay. At what angle and bearing should the pilot fly to actually reach Albuquerque? So here we're talking about they want to fly in this direction. Okay? And they are going to go in this direction at 250 T. And our wind is still going to be blowing at 20 T in that direction. And that's a horribly not to scale drawing, but I think it does the job. I want to know what the angle should be. So if you think about, for any t, I still have this right triangle of 250 over 20, and so my angle, tangent of theta, is going to be 20t over 250t, or those would cancel, and so my angle for this will be inverse tan of 20 over 250. And so to actually show up in Albuquerque, and I think this is a slightly different angle than the angle they were traveling. The angle they were traveling was 4.57. Oh, that's the same. Oh, I know what my mistake is. I knew I made a mistake because it's not supposed to be the same. My mistake is I don't have a tangent here. I have opposite and hypotenuse. So it's not a tangent problem at all. It is a sine problem, which means that my answer will be inverse sine of 20 over 250. And it's similar, but it's 4.589 degrees. How long will it take to fly to Albuquerque? So if we think of our triangle again, here's our 250t, right? Here's our, this can be split up into two parts. Let's try that again. A 250t in this direction, this right here, this x component, is going to be the 250t cosine of my 4.589. And this piece would be the 250t sine of 4.589. And the 250 times this will give me my speed in the x direction. And if I know my speed in the x direction, I can figure out how long it will take me to get to Albuquerque. So if we take our 250 cosine of that answer, so our actual speed in the horizontal direction is 249.198. And so to go 1,000 miles horizontally, I will divide by that answer, and it will take 4.013 hours. And that's our motion problems using parametric equations.